Bridging the quantum divide. The macroscopic discovery that earned John Clarke, Michael Devoret, and John Martinis the 2025 Nobel Prize in Physics won the antecedent, a question of scale. For decades, the peculiar laws of quantum mechanics, such as tunneling and quantized energy levels, were confined to the microscopic world of atoms and elementary particles. Classical physics reigned supreme on the macroscopic scale. However, a major question persisted. Was there a hard boundary, or could quantum effects be observed in a system large enough to be held in one's hand? Theoretical work, building on the concepts of superconductivity and the Josephson junction, suggested a macroscopic quantum object could, in principle, exist. The challenge was to find it. To the breakthrough. Experimental proof at Berkeley. The critical phase of discovery took place in the mid-1980s at the University of California, Berkeley. Professor John Clarke, a pioneer in superconducting electronics, joined forces with his doctoral student, John M. Martinis, and a visiting postdoctoral fellow, Michel H. Devoret. Their goal was to move beyond theory and provide definitive experimental proof of macroscopic quantum mechanical tunneling, MQT. The apparatus they devised was a superconducting electrical circuit, tiny by conventional standards, a chip about a centimeter in size, but macroscopic in the quantum context, involving billions of particles. The core of the device was a Josephson junction, where two superconducting layers were separated by an ultra-thin insulating barrier. Classically, an electrical current should be trapped, unable to cross the barrier without an applied voltage. However, operating the circuit at ultra-low temperatures and with meticulous precision to shield it from environmental interference, the team began to observe the impossible. The system, which could be modeled as a collective particle, was managing to tunnel through the potential barrier, escaping its initial zero-voltage state and exhibiting a sudden voltage. This was not a thermal jump, but a genuinely quantum process. MQT, confirming the collective charge in the circuit was behaving as a single macroscopic quantum object. 3. Confirming energy quantization. The work didn't stop at tunneling. Quantum mechanics also predicts that energy in such a system should not be continuous, but exist in discrete, or quantized, levels. Clarke, Devoret, and Martinis also succeeded in observing this phenomenon in their superconducting circuit. They demonstrated that the system absorbed and emitted energy in specific, discrete packets, precisely as mandated by quantum theory. This joint demonstration of both MQT and energy quantization in a human-made electrical circuit was the undeniable evidence. The line between the quantum and classical worlds had been blurred. The circuit, despite its macroscopic scale, was demonstrably governed by the laws of quantum mechanics. For the legacy, foundations for quantum technology. The immediate result of the Berkeley experiments was a fundamental advance in physics, establishing the field of macroscopic quantum coherence. In the periodic evolution of science, this discovery served as the crucial launchpad for a new technological era. By proving that engineers could fabricate and control a macroscopic quantum system, Clarke, Devoret, and Martinis effectively laid the groundwork for modern quantum computing. Their Josephson junction-based circuits, which functioned as artificial atoms with controllable quantum states, became the blueprint for the superconducting qubits used in many of today's most advanced quantum processors. This leap from a fundamental physics question in the 1980s to the emerging technologies of quantum cryptography, quantum sensors, and quantum computers is the powerful evolution that the 2025 Nobel Prize recognizes, a scientific triumph that continues to shape our technological future.